All right, so we begin now. So we have the following reduced setup for the classical obstacle problem by subtracting of the obstacle, and we are just dealing with a quadratic obstacle, okay, which is this. And then what we showed so far was that U is C11. Second, the non-degeneracy estimate, that is if 0 is in the free boundary point, so the free boundary point of U is the set where U equals boundary of the set where U equals 0, and this is also written as boundary of the coincidence set, so that in one you have two notations, okay. So lambda U is the set where U equals to 0, the boundary of that is the free boundary, okay. So this is now our point of interest, okay. So we want to understand the structure of the free boundary, where you make the transition from 0 to solving the equation of n equals to 1. Okay, so this is a hard problem, right? I mean, theory, the Laplacian can be very simple at at least we have been able to transcend a lot and be able to prove that U is C11. Because if I just apply the basic elliptic theory, I would just be having that U is in W2P for all p less than equal. C11 is a good application, and that is because you have a one-sided constraint that U has to be above the obstacle. So that forces that bad oscillations cannot happen, as you will hook up. Okay. So the reason as to why the singular integral theory, the Calderon-Zygmunt theory, fails at the end point is because of these oscillating functions. But that are not allowed in this case because of this one-sided constraint that U has to be bigger than equal to 0. Okay. So now, if you have a non-degeneracy estimate, that is, if I take any ball, okay, supremum of U over dr is equal to Cn r square. So this is another thing that we had, and this Cn does not depend on U, okay, in any way. And what did we show? We showed the finite perimeter of the free boundary. Then I said that for understanding further regularity properties of the free boundary, I drew parallel with the theory of minimal surfaces. The reason as to why I did so is because Caffarelli, as he said, was largely inspired by that, and you will see several sort of analogs of these arguments. So what do you do in the case of minimal surface? First, you solve the problem in the variational way, so that is the soft part of the theory, and then you want to understand better properties, okay, of how good the minimal surface is. So what you do is that at a point on the minimal surface, the area minimizing surface, okay, you zoom in. And then you have a scale invariant quantity and a monotonicity formula that allows you to tell that once you zoom in enough and enough, the blow-up limit is a cone. And then there is a classification of cones in dimension less than equal to 7 that tells you that they can only be hyperplane. So that means that if you zoom in the minimal surface far good enough, then it is closer and closer to a hyperplane. So that means that the minimal surface along a certain direction is very flat. And then comes the Banerjee's famous theorem, which is flatness implies smoothness. Okay, so once a minimal surface is flat, then it's smooth. So this is the kind of the strategy of a very gigantic theory of minimal surfaces, which is a combined effort of Allard, Banerjee, Leon-Simons, and so on. Okay, so we will try to adapt a similar strategy here. So therefore, you see that one key thing that led to that was that you had some understanding of global solutions. Okay. So in the context of this, we also want to understand what the global solutions are. Now, my claim is that if I have, and this will take inspirations not just from the theory of minimal surfaces, if I were to give motivation, a little bit more motivation, it would also take sort of inspiration from the potential theory. Okay, so Luis Caffarelli was largely inspired by many such related development, but of course, the ideas are incredibly original. They are a significant push from the what was known prior to that. There is no harm in saying that. Now I want to tell you that suppose this is the set where U is bigger than 0, this is the set where U is less than 0, or U is equal to 0, this is the free boundary point. Now I want to say that a point where I can touch it from the positive set by a ball, okay, at this point, the second order expansion should be positive. That is, at this point, if I rotate coordinates, I should be able to write U to be summation AI xi square, where all ai's such that for all ai is bigger than equal to 0 for all n. Which is to say that nearby, because when I zoom in, so how will I zoom in? So you see that this gives me that U decays like CR square if 0 is the free boundary point, and this is the estimate from below. So this will tell me that UR of x, the right scaling is the quadratic scaling for this classical obstacle problem. So there will be a non-trivial limit across a subsequence, right? Across any subsequence, there will be non-trivial limit. The hard part is that across different subsequences, there could be a different limit. So what you can have potentially have is that there could be some logarithmic spirals, right? Or a mosquito coil. But of course, not a finite mosquito coil, but infinitely rounded in different ways. So along different subsequences, the limits would be different. So this is a big fight in this theory. How do you rule all of this out? Okay. So that is a great development that happened in this theory. So, okay. So the thing is that if you see that if you sort of zoom in further and further, this will be what? From the positive set, use real analytic because Laplacian equals to 1. So near that, heuristically, you will have a quadratic part and a third order part, right? But when you divide by r square, the third order part will diminish. So this will be the blow-up limit. So this is expected to go at least at these points to ai xi square if the origin is a free boundary point, such that origin is touched by a tangent ball from the positivity set. This is my claim. I want to say that at these points, all the second order part has to be strictly positive definite, okay, or positive semi-definite. It need not be strictly positive definite. All you need is that all these entries are positive, non-negative, and the sum of these AIs should be equal to 1 or 1 by 12. Okay, so that the Laplacian of this is 1. Okay. Now, why is it so? Well, it is so because I don't know why I'm using this. If this is not so, then what will happen is that if suppose A1 is less than 0, okay, and this is say the tangent ball, and say this is the axis of A1, okay, then there will be a cone of negativity around A1. So this polynomial ai xi square will be negative in a cone of direction around x1 because in a very small angle, the xi part will dominate over all other things, right? The x1 part will dominate over all such, okay? In a cone of direction, this will be negative because this will dominate over all, assuming that a1 is strictly less than 0. So in a small cone, this will be more negative. And because this is the summation ai xi square is the approximation of u, it means that either u has to be negative here, which is not allowed because u is having this constraint that u is bigger than equal to 0, has to lie above, okay, this obstacle condition. So that means that this free boundary has to leave outside the cone. And so therefore, these are not points where you can touch it by a tangent ball. Okay. So this is really an idea that is inspired by similar considerations in potential theory, which says that if I give you a domain, okay, the properties of the harmonic measure are decided by good points where you can touch it from tangent ball from inside, because these are the points which will have good harmonic measure. Okay, so if you start a Brownian motion somewhere, so you will have a good probability of hitting at this point. On the other hand, if I have these kind of points, and if I look at this side, okay, then you see like if I start a Brownian motion here, then it is very unlikely that it's going to hit here, right? With much lesser probability because there is a narrow spike, skinny spike that is going. So these are points of very little harmonic measure. So therefore, the good properties of the domain are decided by those which are where you can touch it by tangent ball, okay, from the inside. Okay, so again, this is just the heuristic. So I don't know, I mean, how he even came up with this whole idea of proving the convexity, because a priori from the situation, it was not even clear that convexity is the way to go, but finally it turns out to be, okay. And what is incredible is that I will show you the scheme of arguments, how it goes, then cone of monotonicity and everything, which he developed in 1977 and 1980. That is behind the other part that Sandeep mentioned in his lecture, which is the ball version where you have asymptotic symmetry, where you don't go to infinity, where you have to enlarge the cone of monotonicity, the directions where you can sort of move, okay, the tangent, the moving plane, okay. Every time the monotone direction that keeps on increasing. If in a certain ball it is something, then in half the ball it is more, and that you will also see similar glimpses of these ideas when I do the Monge-Ampere or when Debabrata does some further results on regularity of optimal maps, okay, under some conditions on the support of the density, okay, on the supporting measures of the target measure. So anyhow, so let me not go into any further motivation. Let's go to the proof. First is that I want to understand how the second order part will grow near the near such point where you have a tangent ball, okay. So I have this, so I will exaggerate this picture a little bit more so that I can draw these sort of balls like this, okay. This is a ball of size 1, and say this is origin. Okay, it is in some direction ball of size 1, and I know that my whole situation is scale invariant. If I am able to say something in ball of size half from this, then I will be able to do it at any scale r, because this whole situation is scale invariant. So anyhow, so that will come later. So what I do is that I take a point here at a distance h. Then along any direction e, I will have either e will move inside or minus e will move inside, right? Move inside this ball, because it gets flatter and flatter, right? So either this will move inside or this will move inside, one or the other. Either e will move inside the domain or minus e will move inside the domain at this point. Let this point be h of en, okay? Either e will move inside or minus e will move inside. The most dramatic situation. So the idea is that you want to move inside the domain so that you are far away from the boundary. So this is the llama. So the most dramatic and the worst case scenario would be it is sort of vertical. Okay, that is you are getting close to this tangent ball. But in anyhow, suppose you move along this direction. I know that if this is h, this is like square root of h, right? This is the property of the ball. You have the parabolic scale, right? So if I move along this, so this is more like I take a point x. So let me call this point x only, okay? And what I do is that I move x plus h half of e. And now what I want to do is that I want to compare the values of u at this point and this point. Okay? So now u of x of h half of e will be equal to u of x plus grad u of x dotted with h half of dotted with h half of e plus the Hessian half maybe computed at some intermediate point. Okay, so which I can write it as an integral, and then it will be h half square. Okay, so don't look at the inside. Okay, this is insignificant, but this is how you write the Taylor expansion. Okay, of order 2. Clear? So now the thing is that I know that this quantity over here, because I am inside the positivity set, is bigger than or equal to 0. So this I can replace by this quantity. I can replace by max of. So this is along UEE. Okay, because I'm just moving in this direction along this. Okay, so max of UEE times 8. So therefore, what you have is that max of UEE along this line, okay, along this line L times h is bigger than or equal to minus grad ux. What is with h half? I'm taking the modulus, okay, plus minus u of x. Now this is at most growing like in this region like h square, and this right, because this distance is like h, so the quadratic decay will tell me that it cannot grow more than h square. So how negative can it be? At most minus h square, and this quantity is how much? This quantity is h to the 3 half. So this is going to win over this, right? So this is more negative than this. So once I put this together, I still gain something. So what I gain is the following, that max of UEE over this H is bigger than or equal to times H is bigger than or equal to minus H to the 3 half. So if I cut this, this becomes minus H to the half. Great. So I know that there exists some point over here. There exists some point over here where UEE is bigger than or equal to minus H to the half. Okay. Now, what I do is the following. I look at the minimum, how below UEE can go. Okay. So suppose I have what to say. Suppose UEE in this region is bigger than or equal to minus alpha in this whole ball. Now I know what I know is that UEE plus alpha will then be bigger than or equal to 0. So let's call this V. But now I have more information about V at some point over there. And that is going to reflect in my positivity, which is to say that V at some point, let's call this point Y, and there is a point here where UEE crosses minus H to the half. So if I put this information here, I would get that V of Y in this somewhere inside the ball is bigger than or equal to minus of H to the half plus alpha. Right? Clear? Now what I do is that I take H to the half comparable to alpha by 2, then I can say that B of y is bigger than equal to minus alpha by 2. So that is at some point I gain some positivity plus alpha by 2. Okay, so I can get rid of one and then still keep this here. Okay, alpha by 2, because there is some positivity that is coming from this, which a priori. So what is the point? The only thing that I know about UEE is that it is bounded from below because of C11 regularity. But now I'm seeing that at a distance comparable to h, UEE is not too bad. It's like minus h to the half. So therefore, if I sort of subtract of the infimum or add the infimum, whatever it is, subtract of the infimum, so the infimum is minus alpha, so you subtract of the infimum, that becomes plus alpha. So you see that you are able to find some point over there where you gain some regularity, right? So, and now comes what? Now comes the Harnack. So now I have, so let me again draw this picture because picture says million words, okay? Picture simplifies proofs as it does, as it does in Luis Caffarelli's theory. So the hard part of reading Luis Caffarelli's papers is to unravel those words and put them in pictures. That is the only way of understanding Luis Caffarelli. If I were to say, I mean, so of course there is an analytic portion, but again, that also has to be sort of visualized in an appropriate setting. So what happens is the following: that I have some point here where I gain something, okay, which is to say that at this point, at V of y over here, so this V over here is bigger than equal to 0, but on this part, V is bigger than equal to alpha by 2. And now what Harnack does is that if you have non-negativity everywhere and V is harmonic, why? Because Laplacian U equals to 1. So in the region where U is bigger than 0, which is inside this tangent ball, V is harmonic. Is it clear? V is harmonic and V is non-negative because I subtracted of the infimum. But I have an additional gain. I have a gain that at this point, I don't know where, somewhere inside, V is bigger than equal to alpha by 2. And what Harnack does is that if it is non-negative everywhere, it sees a positivity somewhere, it ensures that the positivity is perceived in a uniform way in half the set. And as in the proof of the Carlson estimate, you will see that this would imply by this chain of ball that V has to be large in a powered way compared to alpha. So remember, like when we took a point where the value was m, that distance was like m to the minus epsilon. So therefore, if I see the value alpha, so in half the ball, this information would tell me that V has to be bigger than equal to alpha to the m. Or said differently, this implies that UEE is bigger than equal to minus alpha plus alpha to the m in B half. Half of some E. So E is some center point. This is 0, this is E. Okay? And now I can, because this is a scale invariant estimate, I can state it in the following way. So suppose lemma, so this is the gain in positivity, right, in half the set. Because I am able to see some point where it has to be bigger than what the worst case scenario is by a good amount. Something which goes to 0 as h goes to 0. Okay. So lemma is that suppose you have the same situation, U as in dot, U as in our discussion, okay, with nothing else, such that 0 is the free boundary point and PR of some E touches 0 from U bigger than 0. Okay, so let alpha be equals to supremum or infimum of UEE for any direction E in PR. Well, I should not call it E. Let me call it some X0. Okay. So what this gives me is that then I have that UEE is bigger than equal to minus alpha plus alpha to the m in BR by 2 of X0. This is the scale invariant estimate. Okay, and now you see that how we gain. Okay, this is all thing. So now here is the thing. So now I want to show claim that if 0 is a free boundary point, then I want to say the following, that if I take any UEE, it has to be bigger than equal to has to be bigger than or equal to minus UK plus okay, so if it is bigger than or equal to UK, where UK is bigger than or equal to mu k minus 1 plus mu k minus 1 to the m. This m, and this m is the same m as in over here. So this m is a universal m which only depends on the Harnack constant. Remember, like when we did this chain of ball to move inside, I just captured something where this c is like log 2c, right? As in the Harnack. Clear? It's a log of the Harnack constant. Okay. So this is what I have to show. And how do you show? Well, suppose I know the information somewhere. So what is it telling you? That every time you are able to lower, go above the negativity set. So this is a recurrence relation, right? Because it means that mu k is less than or equal to mu k minus 1 and so on. Sorry, other way around. Mu k is bigger than or equal to mu k minus 1 and so on. And this has to stop at 0. Because if it stops somewhere which is less than 0, then again I can improve it by this one. So I'm sorry, minus mu k plus mu k. I hope this is clear. Okay. Well, I don't know what to, so okay, so what I will do is the following. I'm getting confused. So if I will show that if is bigger than or equal to 1 by 2 to the k, then 2EE is bigger than or equal to minus mu k plus mu k to the m. And this is my mu k plus 1. Clear? So that means that at every time I'm able to lower the negativity. So, in smaller can be 1 by 2 to the k plus 1. If 0 is a free boundary point. Okay, so in every ball around 0, if I go at dyadic scale, at every time I'm able to improve this negativity. So let me not worry about pluses and minuses. I will keep making mistakes, so it is open to interpretation. Okay. So now how do I do it? Well, not much to do after what I have already done. Is that you take this point, this is the 0, and suppose x0 is somewhere over here. So suppose x0 is in the next cell. And because I know that the distance of x0 from the free boundary has to be less than 1 by 2 to the k plus 1, because 0 is already at a distance less than 1 by 2 to the k plus 1. So take whichever point, okay? So if I take the ball and then I take this ball, okay? So wherever it hits, there I can put a tangent ball. That is the good thing about this theory. Now you see why these are good points in the potential theoretic thing, because if you take a point far away and you want to compute the harmonic measure, you just look at the nearest point, which will be like more or less like the normal. So you will only be hitting good points of the boundary, where you can make sense of this Poisson kernel. Okay, at least in the roughly in the smooth case, where you expect that the harmonic measure is very good, right? Which is the derivative of the Green's function or any Martin function. Okay, so this is what. But now this distance is less than or equal to 1 by 2 to the k, 1 by 2 to the k plus 1. So the whole thing lies in 1 by 2 to the k, 1 by 2 to the k. So this ball, this B is contained in B 1 by 2 to the k, right? The previous ball. Here, triangle inequality. So now, here I know that UEE is bigger than or equal to minus mu to the k in this whole ball. Why? Because it is in 1 by 2 to the k, the bigger ball. And then if I apply that property as over there, in half the ball, by Harnack, I will improve the positivity or lower the negativity. In this ball, I will have that UEE is bigger than or equal to minus mu to the k plus mu to the km. This is the universal m, depending only on the Harnack constant. That means to say in particular, it implies that UEE of x0 has improved by this amount. And x0 is an arbitrary point in half the ball. And so therefore, this is a recurrence relation, and this recurrence relation has a limit which is 0. Because if you stop somewhere before 0, then again in the next step, you can improve by mu k to the m. Make sense? So therefore, you have been able to show that as you get closer to the free boundary, the secondary, the Hessian starts becoming more and more non-negative. Okay? Good. So this gives me, so in fact, if you want, I can write down explicitly what this modulus is. But you don't need to do, because you know that there is some modulus of continuity. This kind of a modulus is more like, so you are not able to improve. So this is not Helder modulus. In the Helder would be at the next step you improve, some amount of mu k. But here you are improving mu k to the m, and then it's a very trivial exercise in high school algebra that this is like a log modulus of continuity. This should be clear to all harmonic analysts. So that comes so often, right? Not necessarily PDC, but depending on what you do. But it's an exercise. Okay? It's about what you keep using all the time. So now, okay, so now I've been able to show that. So now I define my solutions. Okay. So if I have U is suppose a solution in B1, and 0 is a free boundary point, and I will have an assumption, global assumption on B1. And now I define, so this class I will define, well, C, let me keep it for something else. This class will be P1M. And in general, PRM will be class of all solutions such that Laplacian equals to this in BR. 0 is a free boundary point, and d square U has, okay? And T infinity M will be 1 where you have a global solution with the same Hessian bound. Anyway, the quadratic decay tells you that the global solutions cannot grow more than quadratically, right? And well, coupled with the non-degeneracy estimate. If you put both of them together, then you can only have a quadratic product exponent. Okay, so this is one. So similarly, P infinity M, which is a global solution. So now what I want to say is the following. So for C1M, now this whole family of solution is compact, right? So and all these modulus of continuity that I got are universal. They are only dependent on the Harnack estimate, right? And the bounds on d square U at the very beginning. Okay. So therefore, what I want to say is the following, that in this case, what you have is, in this particular case, you have that there is a universal modulus, sigma m, such that d square of U in BR, such that for any pure second derivative, this is bigger than equal to minus sigma m of R for all x in BR of 0. Right? So there is a universal modulus of continuity. One is that you trace this modulus to be only dependent on the bound on the second derivative, and the rest is Harnack. So it is a uniform one. Even if you don't believe it, you know that this family is compact. So whatever is estimate is true for one. Which M? I'll forget that M from now on. Okay. Once that I prove this. Okay. So I will not say. No, you have a good point. And I don't know how to fix it. If I put n, that may mean something else, right? So whatever it is, so the thing is that whatever information is for one, because this whole family is compact, by Caffarelli's meta theorem, you can make it uniform in the whole family, which you don't need in this particular case, but I'm just telling it because I will need it later for the Monod theorem. Okay? Good. So now what can I say about this PM? So if it is this PRM, then what I do is that I take QR of X to B. So for large R, I'm not zooming in, I'm zooming out, right? Blow down. Then UR is in P1. So d square of U, so d square of U, UR is bigger than equal to minus sigma R for all R. Okay. And now what you do is that you take R to be 1 by R. Right? Because this is defined. So in the original one, you if you take, so if U is defined in then U R of X to be U of Rx by R square is defined in that, right? So is it clear? So this is fine, right? So now what I do is that if I start with U and I take U R of X to be U of Rx by R square, then UR is defined in P 1 by R. Right? Clear? So as R is small, so it's defined in a larger region with the same quadratic decay. So let me just try to fix it. What exactly I want to do? I want to connect this both. So I want to say the following, So okay, so this is fine. So okay, so sigma R. Okay, is bigger than sigma r of, okay. So then, so I'm just through. So just let me see that what exactly I want to say over here. So that you are. So I just need to quantify this a little bit more. So in particular, if I take r to be 1 by r, this will tell me that this estimate will give me that d square ur is bigger than equal to minus sigma. D square ur will be bigger than equal to minus sigma 1 by r, right? So let me continue this. But d square is b1 by r. Agreed? But this is exactly d square u in b1. This quantity d square ur in b1 by r is exactly d square of u in b1, because if I take two derivatives, r square go away, and then r into 1 by r is like b1, right? What I'm trying to say is that d square u r in b1 by r equals to d square of u in b1. Okay, clear? So then what I have is the following, right? So then what I have over here is that therefore d square of u in is bigger than equal to minus sigma 1 by r. Agreed? So now if I let r go to infinity, which is p infinity m, which is global solution, I get that all global solutions are convex. So r going to infinity, then I get that d square of u is bigger than equal to 0 in b1 for u in p infinity n. But then the thing is that there is nothing special about b1. I can make it any bk, and I will have that d square is bigger than equal to k by r in pk. Right? There is nothing special about b1. So therefore, I can sort of spread. Other way to see it is by analytic continuation. Once you know that it's bigger than, well, I'm sorry. So you see, so and then you can let this r go to infinity. You see, there is nothing special about b1. I can do it for any k. Yes.
Why is sigma 0 equals 0?
Because of this. Because it is a recurrence relation which never stops before 0.
So the thing is, let's say m is power 10, right? So minus half plus half power 10, and then you're doing again and again.
Yes.
It's going to 0.
Yes, it has to stop at 0, because if it stops before 0, then again in the next step you can jump up.
But it might not achieve the minimum, maximum, right? It can go on and on and on, but not reaching the optimal point. It can still go on.
Even if it does, but it goes as close to 0 as I want. I don't know whether I want to achieve it. All I'm trying to say is that if I take smaller and smaller balls, because I'm improving this in a fixed amount,
yes,
then it is going to 0.
My doubt is that, let's pretend we are looking at minus half, right?
Uh-huh.
So we're looking at minus half plus half power 10.
Okay.
And then you are adding plus minus half plus half power 10 power 10.
Yes, so that has to stop at 0.
Extremely small.
Yes.
Compared to minus half.
Yes, but at the next step, you don't raise the power even more. You keep the same m.
Power, but because half is so small, half power 10 is much smaller than half.
Okay, so one thing you see, because it's a monotone sequence, it has a limit, right?
Yes.
Agreed?
Yes.
So I should write it for, so mu k plus 1 is equal to actually mu k minus mu k to the m. So it has a limit. So if I take the limit here, and limit here, it doesn't have any other choice but to be 0.
Okay.
Okay? Yeah, so I get that. So now how do I apply it to my situation? I'm sorry, so I described this. This should come after this. Okay, so I just don't want to relate all together. So if I have a global solution, so therefore what I get is that if u is in p infinity m, then u is convex. And this is going to be the exact analog of the fact that global minimal surfaces are cones. Okay, this would just be the substitute for that will put us in the right sort of framework. Okay, so this was a big fight that Caffarelli had, that he was able to sort of put this, but again now you have to put it with other ingredients all together. Okay, how fast I'm approaching a global solution. So now what happened? So now this u is convex. So now if I start with u in p1, and if I take ur to be ur of x over r squared, then this is in p 1 by r, right? So I'm just trying to isolate things. I'm not putting all together. First, I am showing every global solution is convex. Then I am showing that the blow-up limit is convex. Okay. So when you try to club together, this is what happens. So once you have this, so therefore you get that UR goes to some U0. Why does UR go to U0? Which is in P infinity of n? Because of stable estimates. So let's look at those estimates. So at least in B1. So you see that because of the quadratic estimate, UR is less than equal to C in B1, right? Because R square and there is a decay that is R square. So that catches the singularity. DUR is what? 1R comes out and 1R goes in. So it is like du of R of x by R, but this grows like at most like R near a free boundary point. So this whole thing is also bounded. And d square u is the same. So you have uniform C11 estimate. So this converges in C1 alpha in B1. And it not only converges in B1, it converges in every compact subdomain. There is nothing special about B1. So what I get is that if I take this UR, so UR along, so this blow ups along any subsequence converges in C1 alpha in compact subsets Rn global convex not. Okay, that is what I prove on any compact subset, because I can take an exhaustion of the domain. There is nothing special about B1 which converges to a global U0. Okay, so now I want to say that what can I say about this U0? So now I will try to split my cases. Now I will so what is one situation? One situation would be, which is an ideal situation, is that I have this to be the free boundary, because if there is no free boundary, there is nothing to study. And this is how the origin is this free boundary point. So all of these are under the assumption that U is in P1. So where did I define P1? Origin is the free boundary point, because I just want to center at the origin. So at this point, if I zoom in, you see that the limiting profile is a tangent plane. Suppose there is some regularity over here, right? So that means that the limiting profile has to be, if this distance is set, if this is like En, the limiting profile has to be 1/2 xn plus square, with no other option, right? Because as you zoom in, you get closer and closer to the tangent plane. If you want to have some regularity at this point. So that means that on this side, U is bigger than equal to 0, and on this side, U is equal to 0. So if I take a ball and take any ball around it, there is a good chunk of the coincidence set. And not only that, the minimal diameter of the coincidence set is comparable to 1. So now I will have a lemma that, so therefore, in order to get any regularity, you have to have a quantified assumption on the free boundary point that at that point, the minimal the coincidence set is largely measured. And this will be done quantified in terms of the minimal diameter. That is another idea. So there are various ways of doing so, but this is one way to sort of. So one thing, let me tell you, the non-degeneracy estimate tells you that the following cannot happen. That is, it cannot be that. So the non-degeneracy estimate tells you that you cannot have a picture like this, that this is the zero set. Why? Because if there is a non-degeneracy, you see, like as you get close, I mean, you cannot retain the quadratic picture. So, but what non-degeneracy does not tell you is that this kind of a thing can happen. This is a coincidence set and this is a positivity set. And these kind of examples do occur. So there are slits. And the Sheffer has some counter examples where there are points which could be singular. Okay? For the classical optical problem. So, and why are these points bad? These are points where the coincidence set becomes skinnier and skinnier in measure. Right? If I take any balls, you see that at this point the density is 0. So now this is what I will do. So I will know that I know how to identify with UR by this. That means that if I start with a local solution, if I zoom in enough, I can approach a global solution. But not only I want to approach the global solution in the C1 alpha way, I want to retain the good chunk of the zero set. Okay? So that would be my next lemma. So it is just that true, the exception. So I define the minimal diameter of a set to be, so I don't even define. So if I have a set this, so let me sort of exaggerate in a certain way. You take all planes covering this, okay? And then you take the minimal one, okay? in the case of an ellipsoid, it is a minor axis. Okay, so this is my minimal diameter. So this length is the minimal diameter of the set E, which is the ellipsoid. And now here is my lemma. So given a bound, so given sigma, this is a bound on the minimal diameter. Okay, there exists R sigma large such that if U is in PR of M, so M is also fixed. Okay, M is the bound of the Hessian. PR of M for all for R less than, bigger than equal to R of sigma, and so minimal diameter of the set I have to indicate with something. So what I will do is that I will define this function to be delta, which is what Luis Caffarelli does. Okay, del of E. This is the minimal diameter of the set E. Such that and delta of U intersection 0 set intersection B1 bigger than equal to sigma or so given sigma, then so given sigma and epsilon bigger than 0, given epsilon and sigma bigger than 0, there exists R sigma large enough such that if I have a local solution and if R is large, I can approach a global solution. I can approach in P infinity M such that UR minus U naught in C1 alpha norm is less than equal to epsilon in B1, and the minimal diameter of the limiting profile intersection B1 also has to be bigger than equal to sigma. Okay, so the fact that if I don't have this geometric constraint, I have already shown by that argument, right? If not, then there exists a sequence of Ri's going to infinity, so which are not epsilon close to any global profile, but then this is a compact family. So in the limit, this will happen and that will lead to a contradiction, right? That is what I've shown over there. You see, like, because what I did about 1 by R, I could have done it for any capital R going to infinity. Look at this over here. 1 by R is like capital R. So 1 by R going to 0 means capital R going to infinity. So it's an indirect argument that if not, then for a sequence of so given epsilon, if not, so there exists some epsilon bigger than 0. For any sequence going to infinity and sigma is fixed, there exists some U's which are which satisfies this minimal diameter condition of the coincidence set, which are not close to any global profile. But that family is a compact family in C11, right? So therefore, it has a subsequence that converges by Arzel-Ascoli in the C1 alpha norm. And then the limiting profile is a global solution, and that is a contradiction for large n of R's. Make sense? So there has to exist an R for every such choices. Clear? The only difficulty is that you have to say that whether this minimal diameter condition is respected or not. And that is not very hard to see.
I'm sorry, can you please tell me what is minimal diameter of a set?
Huh?
What is the minimal diameter of a set?
Minimal diameter of the coincidence set.
What is minimal diameter of a set?
So given a set, you sort of take all parallel planes so that the whole set is a bounded set is contained between these planes, and then you take the minimum minimum diameter. So this is one length, this is one length. So you take all parallel planes which traps that set, and then you take the minimum of that. Okay. So the volume can be large, but this minimal diameter is small. Okay. Yeah. So now, so if not, there exists Rj's going to infinity, such that URj's are not epsilon close 1 to any U infinity. But URj's, and other thing is that URj equals to 0 intersection B1 is bigger than equal to sigma. Because I want to respect this geometric condition in the limit. But URj is going to a U naught which is in P infinity or some U infinity in P infinity of M is okay because it's a compact family. Right? Because I have a uniform bound on the Hessian over here. It's a compact family. And now, so therefore, this is a contradiction to the first part. And the second is that, so U infinity, it does converge. So the only way it violates is that this U infinity global function, this minimal diameter has fallen below delta. But let us see what is the implication of that. So the only way now the lemma is violated is that the minimal diameter of U infinity has fallen below delta. So this is how it can look like. So therefore suppose minimal diameter of U infinity equals to 0 intersection B1 is less than delta. So it is less than delta, but then they are nearby, and this is all in B1 where you have uniform convergence in C1 alpha. But if this diameter is less than delta, it means that U naught here, U infinity here is bigger than 0, and U infinity anywhere is bigger than 0 because this is where the 0 set is trapped. But then for large enough j's at these points, URJs will also be bigger than 0, and here the same URJ, by taking the larger of the j, will also be bigger than 0. But this URJ, then the minimal diameter of all these URJs has to fall below sigma. Because you see, like if this is strictly less than sigma, I can get as close as possible to this this place. And this is a contradiction. So therefore, I have to have that the minimal diameter of the limit should also respect this condition. And what do I now know? That the U naught has to be a convex one, which has come from my earlier estimate. So if I have a good chunk of the coincidence set for the original one, for the zoomed in version, which is a global convex solution, I still retain the same chunk of the coincidence set. So these are the points where I would expect that my surface is real analytic. Okay, but we have to go one step at a time. Now let us try to understand the global solution. What global solutions can be? One global solution is U equals to, as I said, 1 x dot t. This is one global solution. Or you can even have U equals to half ax x, where trace of a equals to 1 and a is bigger than equal to 0. So this is another global solution. But these are not the only global solutions. Okay. Finally, it will turn out that for our free boundary points, the blow-up limits will be these, but there are other global solutions which a priori can be there. So I will tell you that, I mean, there is a beautiful construction due to Hans-Levy where you can get balls or ellipsoids as coincidence set. So what do I do? What do I do is the following. I take the Green's function and I slide a paraboloid below. And it is going to touch it quadratically, and then I continue it by this. And then I get this to be the coincidence set. And this is the global solution. Okay. So I agree. So at the difference, you see, like, I mean, these are harmonics far away from here, but the difference, this has to separate quadratically. And so this is my coincidence set. So I just continue it like this. Yeah. So therefore, this way I can generate balls as coincidence sets. With some more work, you can generate ellipsoids as coincidence set. And there is a conjecture, there used to be a conjecture that in all dimensions, there are only finitely these possibilities. These are the only global solutions that can happen. It is either a half-plane solution or a quadratic polynomial, or where the coincidence set is an ellipsoid, limit of a family of ellipsoids, parabola, and so on. In dimension 2, the classification of global solutions was solved by Sakai, and in higher dimensions, very recently, by combined efforts of Figali, Simon Eberle, George Weiss, and also as Chagolian, Simon Eberle, and Weiss. So people wrote papers in different combinations. So first they settled some dimensional cases, and then the lower dimensional cases were solved by Figali. So that program was completed. So these are in high dimensions. So the thing is that all these you can recover as coincidence sets, which are family of ellipsoids. Okay, whether it be the half plane or even all the other possibilities. Okay, these are because even the half plane can be obtained as a limit of family of ellipsoids, and it was Chagolian's conjecture that these are the only ones. And finally, this has been solved very, very recently, not even a year ago. Okay. So, but anyhow, at the time when Luis Caffarelli was there, this was not known. Okay. So therefore, without knowing that, you still have to work more. So what do you do? And this is often useful because that classification is solved for only Laplacian. But when you are dealing with anisotropic equations, okay, anisotropic, like fully nonlinear equations, it is very hard to have this classification because all these classification results rely on monotonicity formulas which suits the isotropic case. But where different directions scale very sort of non-linearly and differently, like a fully nonlinear PD, you do not even know where to linearize and how to linearize. And there the monotonicity formulas are kind of out of, it's not expected to be present either. Okay. So that makes several questions, including these free boundary problems as well as unique continuation, much harder for these fully nonlinear PDs, and there are a lot of movement problems there. I would not even get into that. Okay, so anyhow, it's always good to have a robust argument where a priori you don't know what the global solutions are. So therefore, let us try to understand, going back to that time frame, how do you argue further, right? So what was Caffarelli's idea? I told you. I mean, it is more like now you are kind of forgetting what we wanted to do because we are doing so many things, but you enjoy the ride because these ideas are just beautiful, right?
Is it obvious how to go from one ball to two decision balls?
What do you mean?
So the bad set can be a ball, you said, right?
Yeah, I think so. I think
decision ball.
So what you can do is that you can take one, you can take the other, slide somewhere, just from the other side of the domain, and then you can just take the whole.
So then what?
Yeah, so I would be able. So if I have this kind of an example, so suppose I want to even generate something like this, I would be able to do it. What? You take U1, which has this as the coincidence set below, and then you take the other one, which has this as the coincidence set, and then you can get all these sets like this. Okay? And then if you overlap this, that is, you take U1 and U2, U1 union U2, that would still solve the obstacle problem, but the coincidence set would have enlarged. What you are saying, I think I can do it if you give me any closed set, okay, not even two balls. So if you give me any back to a closed set, this is something I would have wanted to come later. I don't know if I can do it. I have to think a bit whether I can do it with Laplacian equals to 1. But if I take something like U equals to like D square over here, I can sort of have very different combinations of coincidence sets. So near these, so suppose these are closed sets, and I take like the function which is the distance square from the closed set, then I should be able to get Laplacian U not equal to 1, but a right hand side which is comparable to 1, where you feel like a lot of different such possibilities would be there. Yeah? But again, these are all local. I cannot make it global because the global ones are classified. Okay. But I'm trying to say that although I'm taking Laplacian equals to 1, but you see that in the linearized one, when I grow up, I only capture f of 0 times the characteristic function, which I can take it to be 1. Make sense? Because finally I want to restrict my study to the global solution, which just takes minus Laplacian of psi at the free boundary point. Okay. So now let us understand more. So what do I know? So for the global solution that I have, suppose I have global solution that I have, you have that U0 equals to 0, intersection B1 is bigger than sigma. And now comes the John's ellipsoid lemma. That tells me that if K is a bounded convex, and let E be the largest ellipsoid, such that E is in K, then we have that K is contained in n times E. If you enlarge the ellipsoid n times in all axes, that K has to be contained in this. So I will not even try to prove this, okay? I'll just try to give some idea because n will not be important in my sort of analysis. I can just do with some C. And for that, I think you will be fairly convinced that I have a proof. The proof is the following. So by a affine transformation, I can take this largest key to be a ball, unit ball, centered at the origin. And suppose, so this is the origin is the center. And now suppose this point, which is a part of the convex set, is far away. Okay, so let me draw a picture which is slightly smaller than this so that I can show you the emotion of this argument. So I take a point here. Okay, now if I go too far, then the convex hull would look like this, which has to be part of K. And if this point goes to infinity, it has to be the entire strip. And so if this is very large, I can always trap an ellipsoid with a larger volume that is inside this convex hull and hence inside the convex set. So that means that I cannot go too far. This analysis will tell you that, well, you are doing a planar analysis. Why do you get n? Well, I get n because I am sort of treating that in all other axes, I'm moving in a way which retains the volume. So this kind of a thing, what I'm doing is the following, is that if I have something at 0, this is 0, in the xn direction, I'm shifting the center so that this length becomes 1 plus epsilon. And in order to retain the volume, in all other directions, I'm adjusting the length. So this ellipsoid that I have is something of the type which is x1, xn minus epsilon square over 1 plus epsilon square. I've enlarged this axis, but then in order to have that the volume is 1, because ball is meant to be the largest ellipsoid that is contained inside the convex set after that affine transformation. So in other directions, if you see, I have to adjust this factor, which is 2 over n minus 1 times xi square. And so the thing is that you just want to know the first point where this ellipsoid bulges outside the ball. Okay, if it is inside this convex hull, it's good, but you want to sort of extremize this, and that is more like taking the difference between the two. But difference between the two for small n of epsilon is like taking derivating this with respect to epsilon at epsilon equals to 0. And then what you see is that whenever this happens, when you derivate this, so this you can write it as 1 minus xn square, right? Because they lie on the first point where it bulges outside the ball. And now if you derivate in epsilon and put epsilon equals to 0, what you get is that xn equals to either 1 by n or xn equals to minus 1. Minus 1 means you are touching at, because you started at this point, you are touching at this point. This is 1 point. The other is, this is the xn. This is 1 by n. But then if this is 1 by n, and for this point to be in the convex hull, so the slope has to be less than the slope of this. So you can say that this point is n. So the fact that n is coming up because of the fact that you have to retain the this conformal factor so that the volume is preserved. Okay, because in all other axes you have to sort of adjust by the same amount to retain the volumes. Clear? So I just wanted to tell this because I just wanted to make it look that my first analysis was like a planar one. It should not give you a misconception that you see like the same C works for all dimensions. It is sharp. N is sharp. So now, so how do I use this? So now I know that for my global solution, the zero is a zero set is a convex set, right? And I know that the minimal diameter is at least sigma. So this is the zero set of U0. Okay? And so therefore, if the minimal diameter is sigma, then at least I know that I can trap a sigma ellipsoid inside. Right? So or said differently, if I take E to be the largest ellipsoid inside, if E is the largest, if E is the largest inside, U0 equals to 0 intersection B1. So this is the part. This is the 0. So this is the part. Okay. Then since the minimal diameter of U0 equals to 0 intersection B1 is bigger than or equal to sigma, this largest ellipsoid has to have a minor axis which is at least sigma. The largest ellipsoid has to have a minor axis of diameter at least sigma. Right? Agreed?
That might not be an open set. That I mean, might have a very bad scenario where you have two very disjoint points, and
no, but the zero set has to be convex.
Okay.
Convexity tells that, I mean, you cannot have these see like gaps in between. Okay, so let E be the largest one containing. Okay, so I changed my argument again. So if it is the largest one containing, then the thing is that the minor axis has to have a length which is at least sigma, right? So I would know that 1 by NE is contained in the zero set intersection B1. But if then it means that the ball that I can inscribe inside can be of length at least sigma by 2n. Because if 1 by n is there, so this means that the ellipsoid that is inside has to have a minor axis which is sigma by n, right? But if there is a minor axis of sigma by n, then I can always take a ball with this minor axis, and the ball will have diameter sigma by n, and so the radius will be sigma by 2n. So by application of the fact that the global solutions are convex, the coincidence set is good in size, the minimal diameter is large enough, I'm able to find a ball of a good size. Okay, so what is the upshot of this? Upshot that for the situation, see, like I'm not writing any lemma, any theorem. Finally, you have to all put it together. I mean, if you watch the video several times, at some point I think you can connect the yes. If we want to be bigger than equal to sigma, then there exists B sigma 2 in ball, which is inside the zero set. Some points. And this is going to put us in business. This will give us a cone of monotonicity, which I don't have any time. So what I'll do is that I will take my class at 4:30. So let us try to end the story. I will try to end my proof in 1 hour, in which case I will not do any description of the singular set. But so the 1977 theory of Luis Caffarelli is understanding of these regular points where the coincidence set is big in measure. It's a real analytic surface. So I will show that Caffarelli showed that it is Lipschitz. Then I will apply the boundary Harnack in my first lecture to show that it is C1 alpha. C1 alpha to C infinity is a theory based on autograph transform due to Kindler and Nirenberg and Sprague. But the real difficulty in this problem is to go from nowhere to C1 alpha. That is where the geometric theory comes. After that, it's again a small perturbation theory. And these days, there are modern arguments due to a very beautiful idea of Ovidiu Sabin and Daniela De Silva, where you don't need to apply that formula-based autograph transform. You can do it by higher order boundary Harnack inequality. So I will give a description of that. If it turns out that by the end of the last 1 hour, from 4 at 5:30, I'm just being able to finish this regular part, then I will stop the singular part. This already will give you a good idea of Luis Caffarelli's obstacle problem theory, and then I will tomorrow go to the thin obstacle problem theory. But if I do any better, if I finish that regular part of the story of the regular part of the free boundary in 40 minutes, then I may push like half an hour more to give you what happens at the singular points, and that closes the chapter. Okay, so the lectures have to be improvised depending on what time.